So hello everyone. Next up we have Ed Schouten, and he will be talking about CloudABI. Enjoy the talk.
So hi there, good afternoon. So my name is Ed Schouten. I'm an open source enthusiast from the Netherlands, and today I'm going to talk about how I've been sort of spending my time for the last two and a half years. So first I'll give a sort of a short bio of who I am. I started using open source software back in 2003. That was the year I started studying in Eindhoven, and there was a UNIX users group at my university, and at the UNIX users group was the only place where they had free Wi-Fi back then. So that was sort of a reason for me to become a member of the UNIX users group. But soon I discovered that the free Wi-Fi wasn't everything, and I actually became interested in all of the hardware that they had on display over there. So that sort of got me dragged into hacking on open source software. So what's actually pretty awesome is back in 2004, so that was the first year of my studies, I actually attended FOSDEM. And I counted around a bit, and I realized that this is the 12th time I'm actually attending FOSDEM. So still the conference is all the same. They still have the same stick breads as they had 12 years ago. So yeah, it's a pretty nice conference. So after hacking on open source software for a couple of years, I started using FreeBSD as my primary operating system on my systems. And I became really interested in how it worked under the hood, vimming all of the source code that was stored under user source. Together with a guy from my studies, we actually even ported FreeBSD over to the Xbox One at one point in time, which was a pretty fun project. So in 2008, after sending in enough patches, filling up the bug tracker at the FreeBSD often enough, I was awarded with a SVN account back then, or CVS even still. One of the first BSD conferences I attended was BSDCan 2008 in Canada. And one of the speakers back then at the conference was Chris Lattner. And maybe you've heard that name in the news last week or 2 weeks ago. He's actually one of the founders of the LLVM project, and nowadays he's some kind of compiler tech lead at Tesla, I think. And he gave a really good talk about LLVM Clang, the C++ compiler. So that really got me motivated on taking a look at that compiler as well. So one of the larger things I'd been working on back then was sort of integrating LLVM Clang into the FreeBSD operating system, which is sort of the de facto standard compiler today, at least in FreeBSD. So enough about FreeBSD and LLVM. I'm not really going to talk a lot about those projects today. I'm actually going to talk about what I've been up to since 2014. And this talk is sort of a bit like chronologically structured. So the first thing we're going to look at is what have I been doing in 2014. So back in 2014, I was working as an expat in Germany. I had some time to kill in the evenings. So what I started doing was I was sort of created a Git repo in my home directory and started hacking on some C++ code. I started working on a database server written in C++. And this database server was sort of making use of a whole bunch of things I'd never used before. So I was experimenting with data structures like Merkle trees for making sure that all of the data was consistent, stored inside of it. What was really interesting about this database server that I was designing was that I wasn't using like SQL queries or something to get access to the data, but I was actually loading a full Dart VM in there. So Dart is the scripting language that is being designed by Google, sort of a JavaScript replacement. And I thought that would be pretty awesome to actually design stored procedures in like a high-level programming language like Dart. For replicating transactions across the network, I was using something similar to Paxos called Raft. But the problem with this project is I was only working on this a couple of evenings a night. The other evenings of the week, I usually went over to pubs together with some people sitting here in the audience even. So that project didn't actually make a lot of progress. And in the end, it was just a forgotten Git repo that sort of stayed in my home directory. And it might even be the case that I reinstalled my laptop, so the code is now gone. But it was a really good excuse for me to experiment with all sorts of new technology that I hadn't used before. So just to sort of give you a short overview of how it worked, you had a couple of servers that were sort of connected with each other in like in a mesh, and that would just replicate all the transactions over that would be coming in. And then on the outside, you'd have sort of a swarm of clients and maybe even some caching nodes that would hold on to certain parts of the tree and would make sure that that would all sort of get replicated. So one of the things I was experimenting with this database server was I wanted to harden it. So the problem is you're running arbitrary Dart code in a virtual machine. What could possibly go wrong? You know, it's user-supplied Dart code. What if this Dart code simply contains statements in there that simply say, like, you know, open these arbitrary files on disk, remove /etc/password, etc. So I wanted to make use of sandboxing to actually make sure that even if there would be an exploit in a Dart VM, there would be no way of breaking out of the VM and running arbitrary code. The usage access pattern is quite simple. It either accesses its data set that is stored in some kind of directory on disk. It talks to the other servers in the Raft consensus group, so like the inner mesh, and then you'd have TCP connections coming in from clients on sort of the outside of the network. So what I did back then was I sort of got distracted, and instead of focusing on like getting the database server working, I ended up focusing only on the sandboxing and getting that right, which meant that in the end I didn't have a functional database server, sort of. Completely stupid idea. So I sort of started making an inventory of all the security frameworks that are out there. And I sort of came up with this slide as sort of my observation of like the current state of security frameworks. I'm by no means an expert on them, but this is sort of my interpretation of them. So at the top, they can be sort of divided in two separate groups. Ones that I sort of call static policy-like, and other ones that I call dynamic capability-like. And they have like a completely different mindset of attacking the problem of hardening software. So the static policy-like frameworks, they're sort of built from this mindset saying like, the problem with Unix security is in its security model, namely in the way file system permissions work. So we need to extend on that. File system permissions need to be more complex. There need to be more access control lists on more frameworks provided by the kernel. And good examples of those frameworks are AppArmor and SE Linux, and something that they call POSIX capabilities, even though that system has nothing to do with capability-based security. And those systems, they're typically configured by administrators, users, in some cases even package maintainers of operating systems. So AppArmor security policies, they're typically written by distro package maintainers. They build, what they do is they sort of run the program that they want to harden for a certain period of time, and they sort of analyze it for, say, a couple of hours, couple of days, and the output of that analysis is sort of turned into a security policy that's put in place. So what happens if there's some kind of exploit in it and then that attacker takes over the application, that person can only run the actions that are part of the security policy that was generated during the training phase. So what I've observed is that those security frameworks, they typically only provide like very little gain in security. So the best examples I can give you, for example, a web browser has a file open, file save dialog. You know, whenever you download a file and press Ctrl+S, you get this pop-up box where you can browse the entire file system. Well, that sort of automatically means that this browser needs to be able to access the entire file system of your system. So it basically makes it pretty much useless. Also, what I really dislike about the system is that it's configured by users and administrators, people who have no sort of real deep understanding of how the software works internally. And we sort of expect those people to come up with security policies to make the software secure. Like the software developer doesn't even care about it, sort of throws the code over the fence, and then other people have to clean up afterwards and make it more secure. So what you also see over the last couple of years is that all these new security models, they sort of tend to pop up. And those are more dynamic capability-like. So how it works is that it's not a policy that's sort of installed globally or in the system in /EDC, but it's sort of part of the programming APIs, where sort of the program can say, like, I've acquired all the things that I need to access. I've got my network connections, I can access these paths on disk. Now lock me up and throw away the keys. That's sort of how the security model works. And Linux has this seccomp model. I think the most commonly used flavor of seccomp is seccomp BPF, where they have some kind of OpenBSD pledge. And these tend to have like a really big gain in security, as you'll see in a couple of minutes. So a lot of people ask me whenever I sort of talk about this topic is, where does Docker fit in this picture? And it's sort of a really tough question, but if you sort of look at how Docker is used typically, I'd say it's more like a static system. You know, it's set up by the users to run a program in a confined space. It's not used as sort of an API by programs itself. So now we're sort of going to discuss how Capsicum works. And basically, Capsicum is a sort of two-step recipe for making software more secure. So the first thing that the Capsicum developers have sort of done is they've made the operating system sort of more object-oriented. You could call it like that. So what they've done is they've sort of turned everything into a file descriptor. So normally, there are sort of multiple namespaces that a process can access. It has its file descriptors. It can access the entire file system namespace. Then there's the process table. Then there's the network stack. All sorts of separate frameworks. But what they first did is they sort of tried to unify it into a single, like, scope, file descriptors in this case. So one thing that they've sort of really focused on a lot is having directory file descriptor support, so that you can open a certain directory that's on disk and then sort of say, like, this file descriptor now represents all of the files that are stored underneath this directory. So you can point to subtrees in the file system, basically. And what they've also done is they've added something called process descriptors, where instead of process IDs that are sort of global, system-wide, and you can send signals to them based on some very rudimentary form of access controls, they've changed that into process descriptors. So as you'll see later on, there's sort of a special fork call, PD fork, and that sort of gives you a file descriptor to a child process. And that you can't read or write over it, but it sort of acts as a handle, giving you ownership of that process on the other side. And if you close it, you sort of lose that process. And in practice, that means that that process gets killed and shut down. So the second step that they've sort of done with Capsicum is sort of, now that the operating system is more object-oriented, let's actually let those objects determine what the process can do. So a process can actually give up rights. It can say, I never need to access this certain resource anymore by simply calling close on the file descriptor, and it's gone. Privilege separation. So say if you have this huge program and you want to divide it into multiple sub-processes that all have their sort of separate rights, that's called privilege separation. That's something that you can really easily implement by this model. You can simply fork the process into two processes. One process closes one half of the file descriptor and the other one closes the other half. And then you've really separated the privileges of the process. Another very nifty feature of Unix-based operating systems that a lot of people are unaware of is that you can actually pass file descriptors to other processes. So if you create a Unix socket between two processes, you can use a special message type called SCM writes, where you basically say, I've got this array of file descriptors, now push it through the socket and pop it up on the other side. And if the other side receives those file descriptors, it sort of duplicates them into a different process. So that's also a really nifty trick where you can sort of say, like, I've got access to this directory, and now I need this other running process to write some stuff into it. Well, just push it through a socket, and it comes out on the other side. And what you see as a result of this model is that Unix user group credentials, they become less important. So if you're using Capsicum, even if you run a process as root, it doesn't really matter anymore, because the rights that process has are largely now determined by the set of file descriptors that it owns. So how does Capsicum work in practice? First of all, process starts up like your ordinary Unix process. You can just run it from a command line or from like an init script. At some point in time, the process calls the cap enter system call, and that sort of locks up the process. It switches the process over into something called capabilities mode. And when you do that, a lot of things are suddenly forbidden. So you can no longer open files by arbitrary file names. You can no longer bind to arbitrary IP addresses and port numbers. You can no longer connect to arbitrary hosts in the network. Also, regular forking is not supported because that needs to be done through the PD fork call. The same with killing processes. You can't just send arbitrary signals to processes in the process table. And the same holds for some administrative system calls. So rebooting and mounting doesn't make any sense, of course, if you're in this unprivileged mode. But there's a whole bunch of things that you can still use. So reading on file descriptors, writing on file descriptors, creating pipes and socket pairs. Those are only things that sort of have this local impact. Doesn't have a global impact on the system. Then you can still use the openat system call, which was added in POSIX 2008, which is sort of a special flavor of the normal open system call, but allows you to open files underneath a certain directory. And the same holds for connecting and binding to sockets. They've made special system calls where you can at least say, like, I want to bind a UNIX socket to a certain path under a certain directory. A very important aspect of capabilities mode, of course, is that there's no way of leaving capabilities mode. There's no cap leave system call. Otherwise, the entire security model would be useless, of course, because an attacker could take over an application, call cap leave, and then it could just go on as it normally does. So that's a really important aspect. So for my database server, how you'd use capsicum in this case is it's, again, the same strategy. The process starts up like a regular Unix process. It reads in its configuration file, and in the configuration file, it specifies which directories need to be used and which IP addresses on which we need to listen. So we create all these sockets and file descriptors, and then at some point we call cap enter, and voila. From that point on, we can only start processing requests that are coming in, and we can't do anything else. So for my database server, I started using capsicum, and even though in theory it sounds like a pretty awesome security framework that gives you some really tight isolation, I noticed that using it in practice can be pretty tricky. So it took me quite a long time before I managed to get the Dart VM working within capsicum. That was really exciting. So the reason for this is that you end up with all these pieces of code that are here on this slide, and they're used in practice, and they're simply there, and you'll sort of have to deal with that. So the top one was somewhere in the Dart VM. I think they had some code in there where you could deal with times in different time zones. And if you sort of look and see how you convert times to a certain time in a time zone, you have to use the following sequence. So first you change an environment variable called TZ. You set it to the name of the time zone you want to use. And then what you do is you call this magic function called TZSet. And this sort of reinitializes the C library to use a different time zone. And then afterwards you can call the local time function. So under the hood, what happens, the TZSet function tries to open files under user share zone info. But if you're calling cap enter, then that kind of code no longer works. And what's really annoying is that with TZSet you can't do any error handling. So this piece of code, it still works as it does normally. The only difference is that it still either represents the time in the old time zone that was sort of active before calling TZSet, or it uses UTC or something weird. You can't really tell anymore what it does. And also this piece of code that was at the bottom was also fairly annoying. There is a piece of code that tried to convert a multi-byte string to a wide character string. So what it means sort of in layman's terms, it took a UTF-8 string and it converts it over to Unicode code points, so you can process it character by character. It uses this new lookout function that sort of creates a handle to a localization object. And in this case, it's sort of representing UTF-8. The problem with this function is that it tries to open user share locale UTF-8/LCC type or some file on disk, and it can no longer access it. So this piece of code sort of expects that it can sanely convert UTF-8 over to Unicode, but then it sort of starts to fail. And this piece of code is actually sort of the most interesting one I ran into, and this sort of really demonstrates one of the weaknesses of Capsicum. This is a crypto library you can find on the internet, libtomcrypt. You can find it on GitHub. Put the name of the source file in there. I've reported this issue numerous times to the upstream author, but he doesn't respond. What happens? This piece of code tries to implement a cryptographically secure random number generator. So it tries to open dev_random and tries to read some data from it eventually, but that simply no longer works. So what do we do when we can't open dev_random? Well, yeah, then we just call the clock function to get like the running time of the current process. And that should be used as like the initial seed for all of the random number computation. So we tried to make our application more secure, but by calling cap enter, we actually made it a lot less secure. So what I learned in 2013? Well, sandboxing is stupid and you shouldn't use it. That's sort of my takeaway from it. It's no fun at all. You spend a lot of time figuring out why your program doesn't work. You run into these issues that you can actually only discover by tracing the application system call by system call and figuring out what's going wrong. There's no tooling that actually helps you along the way. You know, you're on your own. Yeah, even if you get it working in the end, you still can't be certain that it actually works in the way you've sort of expected. So I want to sort of close off this part of my talk by putting this slide in there. If you're considering using sandboxing frameworks on Linux SDR right now, or on any Unix flavor, then please, please, please don't use it in any code that makes use of third-party libraries, because you actually can't be certain what those libraries are doing on the inside. And the code in those libraries might actually be changing over time. Upstream might actually re-implement their secure random number generator by something that was shown on one of the previous slides. And your users will simply install the application, install of the dependencies, and they might actually end up with something that's insecure. So this is the reason why sandboxing frameworks work well for Google Chrome browser tabs. They make use of seccomp. And the reason for that is they only run C++ code in there that they've written themselves or maintained themselves or have part of their own distribution. That also explains why Pledge works really well for the OpenBSD people. You know, they typically post these reports saying like, we've ported over so many dozens or hundreds of programs over to use Pledge. It works for them because applications in OpenBSD tend to be fairly small, up to 10,000 lines of C code, and they make use of libraries that are all part of their base system. So that's why it works for them. But this also sort of demonstrates why it didn't work well for me, and it also shows you why if you run PS on your system and take a look at all of the processes that are on there, that almost none of them use any sandboxing framework. So 2014 was over. I moved back to the Netherlands at the end of 2014. My girlfriend and I, we found a new apartment in which we wanted to live, so I was spending there a couple of days in a row, you know, sitting on my knees, putting new floorboards in there, and it sort of gave me some time to sort of reflect on everything that I've been doing in 2014. So one of the things that I sort of realized while I was sort of working on my apartment and getting it all up in shape was this could all be avoided if we simply had a programming environment that didn't have this sort of state transition in it. So where you didn't call cap enter to sandbox, but simply had sandboxing always turned on, where you could sort of assume that the program was sandboxed. So in that case, you could sort of design a C programming environment where sandboxing is always enabled. That's really important. That allows you to remove all sorts of functions that are only work in a non-sandboxed environment. So for example, the open call, you could just remove them entirely. And all of the remaining stuff, you could just re-implement it in such a way that it works well with sandboxing. So it really takes into account that it's running in the sandbox mode. The advantage of having such a model is you can now compile your application, and it will break. It will break in dozens of places, maybe even hundreds of places. But still, you know exactly which pieces of code you sort of need to inspect to get it working with sandboxing. So it gives you this really good guided approach of getting your program sandboxed. You know, you start off with 100 compiler errors of your program not working, and then you sort of keep on working until you reach 0, and then your program works well in the sandbox mode. So, for example, taking this piece of code that was from that crypto library, if you would sort of try to build it in such an environment that is sort of stripped down, you just get errors like these. So your compiler would first throw like a warning saying, like, you know, you're trying to call an open function, and I don't know of the existence of any function under that name. And later on, it tries to link that program, and your linker will throw the error messages at the bottom, saying that it can't actually combine all of the object files of your program into a program, because there's no open function present. So in this case, it's like really trivial to get this fixed. If you'd see a piece of code that tries to do stuff like this, you could just replace all of it by a simple call to functions like getrandom or arc4randomBuff, depending on your operating system. Because these two functions, they can be properly implemented in such a way that they work well with sandboxing. So it's really about just detecting breakages because of sandboxing as early as possible. So what I did then is after I was finished decorating the apartment, opened up my laptop, started hacking again. I went to the page of the POSIX specification. which you can just freely access under this really an annoying URL, so I can't expect you to memorize the numbers at the end. But you can just get this huge list of all of the functions that are part of the specification, and it's like hundreds of functions. And what I sort of started doing was sort of redacting it. So just taking a list and removing everything off it that I thought was either sort of ancient cruft that you shouldn't be using anyway, or stuff that you should only make sense in a non-sandboxed environment, or stuff that only makes sense in this privileged environment. And also added a couple of extensions on top, things that Linux has and BSD has, but it's not part of the POSIX specification. It's a bit sad that that's the case, because in my opinion, the POSIX spec could do a lot better job at sort of catching up with what's being used in practice. And I ended up with this list that was sort of remarkably small. So just to give a comparison, Linux has about 300 system calls. FreeBSD has a bit more, I think 400, around the ballpark. And this environment that I sort of came up with looking at that list, would only give me sort of an operating system that it would only have 60 system calls in them. So that's tiny. Also, the number of data structures that was being used was really compact. So the programming interface for this environment against the operating system was just tiny compared to normal Unix flavors. So what I thought then was, if it's so tiny, wouldn't it make sense to sort of come up with like a formal specification? Yeah, so this is basically what CloudABI is. It's nothing more than a specification of a compact Unix. And it's stored in this nicely formatted text file. Maurice wrote a lot of nice code to actually process that file and turn it into bindings. So it allows you to create C header files, system call tables, and even documentation. And those C header files and system call tables, those are sort of can be copied into source trees of operating systems to provide support. So those bindings are really low level. You shouldn't be using them in practice. This is really all sort of machine-generated APIs. So instead of calling printf, you'd end up with snippets that look like this. But it can be used as sort of a basis for building other things on top. So if you want to build CloudABI programs, you can simply install those header files on your system and use a copy of Clang, should be a pretty recent one, 3.8 or later, and call that in the right way to target CloudABI. If you just make sure that you symlink it under the right names and invoke the compiler under that through those symlinks, then Clang is smart enough to figure out that it should be a cross-compiler. So what I've also been working on is a C library called CloudLibC. I'm really bad at naming things. And it's basically just a compact C library built on top of CloudABI. It implements all of the relevant stuff from POSIX and ISO-C. And compared to normal C libraries, it's sort of different. Instead of relying all of the files stored in user share zone info, it has all of those data sets built in. So that means that it still works well in sandboxed applications. There's also a large testing coverage of more than 900 tests right now. And it works fairly reliably. So here's a list of software I've already ported over to CloudABI. Looking at the time, I had a couple of projects sort of like bold over there that I wanted to look into and sort of show the patches to see how those have been ported over. But I'll keep that as an exercise left to the reader. So what has been ported over, there's sort of a huge variety of things. So it ranges from crypto libraries. Already the start of some GUI libraries have been ported over, FreeType for font rendering and Cairo for canvas rendering. Some database-related projects, so LevelDB, Memcached. And what I'm pretty excited about is that we've also ported over Python 3 recently. So at the end of my talk, you'll get a link to my blog, and there's an article on there on how you can actually run a sandboxed copy of Python even in there. We're also working on getting Django ported over. We can already run some really simple Django-based projects, but there's still a lot of work that needs to be done to sort of make all of it work. I think even templating is sort of still somewhat broken in there and needs some more Python gurus to sort of get working. So what we've done is all of that software that's been ported over has also been sort of pre-packaged. So what we've done is we've created this repository of recipes of how software for CloudABI can be built. One of the things that I really dislike about package collections is that every package collection nowadays has its own package manager. So if you're using Python, then you have to call pip to upgrade all of the software that you've installed through that mechanism. Same with CPAN, CTAN, etc. So what we're doing is we're going in this different direction where we're actually generating packages for different operating systems. So we're creating Debian packages, RPMs, even packages for Homebrew on macOS. And you can install them by simply running sort of the native package manager on your system. It's also really nice because the package names have the architecture in them. You can install multiple copies of them for different architectures. So if you want to cross-compile software for, say, an ARM, it's really easy. Just install like the ARM version of that package and you can compile directly on your MacBook some piece of code for an embedded system, which I think is like a huge plus. Running CloudABI software, there's a bunch of operating systems that support it by now, or for which we provide ways of running it on there. So FreeBSD 11 and later have all of the support integrated. Linux, NetBSD, we have patch sets available for those as well. There's also an emulator available that allows you to run CloudABI programs on unpatched operating systems. So this is what I'm using on my MacBook. I can't expect people here in the audience to recompile the kernel of their MacBook. So there's a simple emulator out there that can at least be used to run CloudABI software. Unfortunately, it doesn't enforce any of the sandboxing under the hood. So if you would write a piece of inline assembly in your code that sort of tries to call a macOS system call directly, instead of going through the emulator, you can bypass security. But it's sort of good enough for testing software before you deploy it over to your Linux or BSD cluster. So running CloudABI software, this is a very simple copy of ls that I've sort of added to the slide. So instead of just reading the directory listing from a directory which you specify in a command line, it simply assumes that a file descriptor, in this case, file descriptor 0 corresponds to a directory, and file descriptor 1 corresponds to your terminal. So if you want to run this, you end up doing this. You end up building it and running it like this. So it's a bit nasty. You sort of pass /etc over on standard in, and voila, you've got a copy of ls that can only access a directory and access your terminal, and that's it. So this works, but it doesn't really scale. Think of the following use case. You've got a web server that can listen on 10 IP addresses and has 40 different virtual hosts, and for all of those, you need one file descriptor. Passing this in on the command line doesn't make any sense at all. It's a mess. So I've been working on an alternative for that called CloudABI-run. And what you basically do is you just invoke it like this. You say, I want to run this executable, and I want to provide it a configuration file of how it needs to be started. And this configuration file is sort of a replacement for command line arguments, and it's sort of YAML-like. And where it differs from YAML, or extends on YAML, is that it's actually, it has file descriptors as a native data type. So consider this simple web server for which you're writing a configuration file. Normally, you'd write something down like this, where you say it needs to listen on this IP address and needs to access these files on disk. With CloudABI run, you sort of add annotations to them where you say, like, this is not a string of some kind of IP address. This really needs to be a socket on which we want to listen. And that's what you do with those exclamation tags that you see in there. That's sort of a standard feature of YAML where you can introduce typing information into the definitions. So what happens is this file sort of gets parsed and gets converted by CloudABI run into this format, namely where all of the files, all the resources are replaced by file descriptor numbers, and this is being passed on to the program. There's also an API for accessing those files from within the program, of course. So instead of using the init main entry point, you now use an alternative entry point called program main, where you have some accessor functions for iterating over maps and dictionaries. Oh, sorry, maps and sequences, and you also have functions for accessing booleans, integers, strings, file descriptors. So what's the advantage of using CloudABI run? You now have a unified configuration file format. There's no need to write your own configuration file parsers. Programs tend to become smaller as a result of using this. And there's also no way of actually accidentally leaking resources into a program. What's really awesome about this mechanism is you can just, as long as you make sure that you're not using any exclamation mark tags for things that you don't want to give away to a process, you can run stuff that you don't even trust. So you can sort of say, like, I'm providing in 2 file descriptors, one of my standard in on the terminal, one of a standard out on the terminal as well. And then the process can only read and write to a terminal and can't do anything else. And that's sort of really ensured by using this utility, that there's no accidental leakage of stuff. Another really cool thing of this mechanism is that it makes programs really easy to test. So because you know what a program is going to access. You also know that it can't actually interfere with your production setup, for example. So if you have a production and a staging setup, you only need to sort of check the configuration file to make sure that you don't list file descriptors that correspond to servers or data sets belong to the production setup. And then you can safely run your process knowing that it won't interfere. So what have I shown you so far in this presentation? I've been talking about the CloudABI project that I've been working on with a bunch of other people. And it's a framework for building testable and secure programs. And it consists of a couple of components, namely the raw definitions of the ABI, the C library that's built on top of that, the package collection for pre-packaged programs, and the CloudABI run utility that can be used to safely spawn those sandbox processes. So now I want to close off this talk by sort of sketching a roadmap for the future. So what is going to happen until the end of times, 2038? So I've got some short-term goals. I'm not saying that they're personal goals, but these are goals for the project, I think, things that the project should explore. So first of all, we need support for more programming languages. Right now, we have support for C, C++, Python, and Lua, I think, so just 4 programming languages, scripting languages. But this needs to be more. Nowadays, you see a lot of people writing software in Go and in Rust and all sorts of other modern languages. We need to sort of be on board with that as well, so we can actually welcome more people into the project. Also, so far, we've had a really strong focus on getting the libraries to work. As you saw in the previous slides, there's a whole bunch of libraries that have already been packaged. But now is the time to actually get full programs to work. We have all of the dependencies ported over. Now we can actually start building full programs. Having a sandboxed MySQL server where you can only sort of say, like, this is your data directory and this is your socket on which you're receiving incoming SQL queries. That's pretty awesome. Same holds for Node.js if you want to run sandboxed web applications, of course. Linux support, right now it's an external repository. This needs to be integrated, period. Or at least the things that we can get rid of need to be upstreamed into the official Linux kernel. So in the end, all of CloudABI support is nothing more than a simple kernel module that you can load into a stock Linux kernel. And of course, there's always the need to improve the documentations, always. And I already have a couple of how-tos on like the CloudABI blog, but we really need to extend on that. There needs to be good developer documentation as well. Long-term goal for the project. So a lot of people, they sort of say to me, like, CloudABI is the stupidest name I've ever heard. It doesn't make any sense. The reason for that is that I often also have to show this slide, sort of explaining the sort of original mindset I had for the project. So CloudABI is a way where you can do dependency injection for Unix programs. And what would happen if you could actually make use of that as part of some kind of cluster management system? So say you want to deploy a pipeline of database servers, web front ends, batch jobs, all of that stuff, and you'd make use of this model. Then you could actually design some pretty fancy stuff. So first of all, you could build some kind of GUI where you could drag and drop programs on a canvas and hook them up through like arrows, say like, this is a web front end, it needs to talk to this database server. You could just click a play button and it would automatically set it up. It would know how to sort of connect all of those programs together. You could also even have like monitoring dashboards based on this concept where, the cluster management system knows the relationship between programs, so it can actually give you accurate monitoring for that. Also, a very interesting aspect is that this kind of mechanism could be used for like setting up the connections between those processes securely. So if it knows that it's going to start up two processes on the same server, it doesn't even need to care about cryptography because it's already sort of secured. Nobody can eavesdrop on those kinds of connections. But if it's starting those 2 processes in different data centers, then the cluster management system could be responsible for creating the keys, sending them over to the 2 servers running the processes. And the server could then automatically set up a secure channel between those 2 processes, which simplifies this kind of management a lot. I've been using Kubernetes a lot, and we have to spend quite a lot of time getting all of the crypto and all of the key exchange right. And this could be sort of solved automatically. So my long-term goal is maybe we could extend sort of tools like Kubernetes to have proper CloudABI support and do this out of the box. So now I'm sort of at the last 1 or 2 slides of my talk. I briefly want to talk about the sustainability of this project. I've been working on this project for 2 years. I had the luck of being able to work on this for 1 full year. Unfortunately, because there is sort of no full-time headcount on this project anymore, the things that I've sort of shown on the previous slide are actually sort of infeasible at this moment. And that's why I sort of, this is sort of like a call for help to the audience. If you think that this is a cool project, at least start using it. Try exploring it, see whether it works for you. You'll quickly run into bugs. Hopefully send pull requests, and it would be awesome if like the CloudABI team can grow, because I think it's a really valuable project. In my opinion, it's still the only solution that allows you to build secure applications just easily compared to all of the existing frameworks out there. So please give it a try. I'm going to give my special thanks to a couple of people. Some of them are sitting in the audience, good friends of mine, who've been sort of either pestering me with bug reports or just giving me mental support, or Katootje, our cat, walking on my keyboard all day long, wrecking my code. I want to thank the people at Kumina BV who've also been supporting me over the last half year and have allowed to sort of work on this part-time. So this concludes my talk. Here's a couple of links. Be sure to check them out. Are there any questions?
So thank you for doing this, because it's really important that we finally get a secure Linux and open source and free software kernel. And my question is, first of all, the problems that you noted were all more or less to do with the VFS. And you basically say you don't have a root VFS, you can't do open. Why don't you do something like a chroot and then bind in the appropriate global state that is benign? And my second question is that you talk about the save issue with Firefox. Why don't you have something like a power box? Or have you thought about how to do a power box?
So to answer your first question, which was why didn't you sort of have a way of organizing the file system layout? So what I've noticed is that this is basically also the mindset that operating systems like Plan 9 have been using. Have proper APIs where processes can sort of create layouts of their own file system namespaces. Everything is done in a file system namespace. But my observation is that it sort of quickly gets messy and bloaty, because so in the case of a file system, what you can do is you can sort of pass it on to new processes, to child processes, to helper processes. But what you'll see in practice is that nobody will bother to sort of clean those up. So then you sort of end up in a state where you have like a bunch of sort of privileged separated processes, but in the end they still make use of this bloaty file system namespace where there's a lot of stuff in there that processes don't need to access. So basically how this differs from what you propose, how CloudABI differs, is that it's a file descriptor namespace. It's a flat namespace. And my hope is, compared to using a file, like a tree-based namespace, is that this will not leak as quickly. That people are a bit more thoughtful about this. Well, maybe it's a bit overly optimistic, but we'll see. To answer your second question, so like the example I gave with the browser, I mean, it's just like a simple example that could like be substituted for any different application. So, for example, your text editor has the same issue, of course. When you're running Vim, it can also access a lot of things in the meantime that shouldn't be accessible. And yeah, that could be solved by making use of different sort of helper tools. But the nice thing about this approach is that it actually enforces the use of a mechanism like that. It's not about just that I've got like a whole solution for that in place already set up, but the idea behind CloudABI is to come up with an environment that sort of forces people to design applications in this sort of privileged separated way. That's sort of, trying to solve it at the root and not at the top. That's what the CloudABI project is about. Did that answer your questions? Are there any other questions? Oh God.
Are you aware of E? And so they have a mechanism called VATS, and that more or less does exactly what you're talking about with respect to automatically creating secure channels between multiple computers over the network and doing consistency things.
So I'm not aware of that project specifically. What's the name of that again? E, just the letter E. That's it. Okay, I'll look into that then. Yeah.
If you look for Mark Miller and E, then you'll find it.
Ah, thanks. Well, then, if nobody else has questions, then thanks for attending my talk. Later today, there's going to be a talk in the BSD dev room where I sort of go into more details on the kernel side of how all of this works. Well, I guess not all of you should be showing up because the room is a lot smaller than this one.
All right, thanks. And that's for you.
Ooh, thanks.
Enjoy.
Ah, no. Yeah, so the charger was mine, not the old speaker.
Did you say the second step was? More about the kernel side?
Yeah. So I'm going to discuss how it sort of works in FreeBSD, how the kernel enforces the sandbox. Because the point is, I originally sort of wanted to give just one talk, but because I wasn't sure I would get into the main track, I also had a backup plan where I did the same solution for BSD. But then both got accepted.
So you have to change the BSD.
Yeah, so I said, one is sufficient. But I thought one talk would be sufficient, but then they forced me to get the second talk as well. Of course. So,
Yeah, it's exciting to hear about the project.
it's in the BSD demo. So I'll be it will be non-stop thinking and sort of showing how it works in the kernel. How BSD is will run it.
Fine. Okay. We don't need to change about it.
Yeah, it's different.
There's no. I think it's a very good direction.
Yeah. I mean, it's also sending RPCs to each other and doing nothing else. Really low hanging fruit with sandbox. So I guess I should pack my stuff before the next speaker shows up. Yeah, but we should chat more today.
Morning.
Yeah.
Now I have a big bird, so for redstone. I do that.
Oh yes, the connector thingy to FPGA.
I do. Awesome. I read the email.
Excellent. We do have this converter, just in case.
I got everything and I tested it.
Great. Yeah, let's get you.
Give me a fresh water.
Oh, thanks. So who's going to get the basal part?
Plenty of time, right? Not
Yeah, I like it.
I'm really planning on attending that talk.